Section 10.4, Part 3, Polar Coordinates and Polar Graphs. Now let's start looking at some calculus with our polar graphs and equations. Now we're going to start by finding the derivative so we can calculate slopes and tangent lines, okay? Now it's important to understand, of course, that when we talk about tangent lines and slopes, it's still the idea of rise over run with x's and y's in a very rectangular field. So in order for us to calculate derivatives to make this stuff happen, we have to view our polar equations in a parametric manner. Now, first off, we're going to express them now as a function of theta. So instead of writing r, we're going to start writing f of theta. But to calculate the x and y's that go into slopes and tangent lines, again, they each have their own conversion from polar coordinates, and this is something we can treat like parametric equations. So our x is going to basically be our f of theta cosine theta, and our y will be f of theta sine theta. Now, again, our goal is to write slopes and tangent lines, so we want to find dy dx. Now, just like we did when we did parametric equations, in order for us to figure out what dy dx is, we have to do two separate calculations. So in this case, again, thinking parametrically, we have to figure out dy d theta, that becomes our numerator, and then, of course, divide by dx d theta. Because obviously we're working with functions of theta, and we have to figure out parametrically change in y, change in x, and putting them together like this gives us that dy dx. Now, what's different, of course, though, is when we did parametrics, these were just simple derivatives. We would calculate each one and create our dy dx. However, because of the way the conversion happens over here, that means that we have to literally find a product rule for x and a product rule for y. Because remember, in the conversion, x is equal to whatever r is times cosine theta, and y is, again, equal to whatever r is sine theta. So in order for us to calculate exactly what this derivative dy dx looks like, we actually have a product rule in the numerator and a product rule in the denominator. So the way this is going to work out is for the dy theta, we're going to do a product rule here. So that means we're going to take f prime of theta, whatever that may be, times the sine of theta, plus cosine theta times our f of theta. Then in the denominator, again, we'll find dx d theta. So now we're doing the product rule here with this one. So that's going to give us, again, f prime theta times the cosine of theta. And then the derivative of cosine, remember, is negative sine. So we're going to multiply that times our f of theta. So looking at the way we find dy dx in polar coordinates, there's a little more going on, okay? Now, obviously, a lot of these pieces we're going to have, and there's a lot of repetition, but sine theta, cosine theta, as well as the f of theta, what our r is, and its derivative all play a role in coming together to give us that dy d theta. Now, a couple important notes. First off, if you want to find where horizontal tangents happen, we're solving, of course, dy dx's numerator for 0, because that's where dy dx would equal 0. So obviously, you're only concerned with dy d theta for that part of it. If you're looking for vertical tangents, of course, that would be where dy d theta is undefined. So its denominator equals 0, which is, dx d theta. So if you simply looking for those points of vertical tangency, that's the part you solve for 0. Now, what's also important to understand is that if dy d theta and dx d theta are both 0 at the same time, then there really is no answer, right, for dy dx. It's indeterminate, right? That's 0 over 0. And that's a situation where we talk about this, the curve not being smooth, right? Obviously, you can find derivatives when you have smooth curves, not at sharp corners. So anytime both dy d theta and dx d theta are both simultaneously 0, obviously, because the derivative doesn't exist, but the curve is still there, that's a sharp corner. So that's a point where we say the graph is not smooth. So let's try our first example of simply writing the equation of a tangent line. Now again, when we write the equation of a tangent line, it's going to look and feel the exact same way as always. So our goal is y minus our y value equals our slope times x minus our x value. We're going to stick with point slope form. Now, clearly, though, we're working with and given, polar equations in the polar system, so we have to do some conversions and then obviously calculate our dy dx in a parametric manner. So first off, let's get the ordered pair, because I don't know x or y or the slope, so let's start somewhere, right? So let's begin by finding our x. Now, remember, the x value is going to equal our r, which is 5 sine theta, times cosine theta. Okay, that's just our normal conversion for that. Now, obviously, what we're doing, of course, is plugging it in when theta is pi over 3. So this is basically 5 times the sine of pi over 3 times the cosine of pi over 3. So if we go ahead and simplify that out, that works out to be 5 times the square root of 3 over 4. Because we basically have 5, radical 3 over 2 and 1/2. So when you put them all together, that's what it looks like. Now to find y, we'll do the exact same thing, only this time, of course, we'll do our r, so our 5 sine theta times sine theta. Okay, so that means obviously we're going to calculate 5 times the sine of pi over 3, and then another sine of pi over 3. So again, putting all those numbers together and working it out, we're going to get 15 over 4. Now, that obviously gives us an ordered pair, so that means obviously we have that part of it. So I'm just going to jot that down. 5 radical 3 over 4 for our x value, and then of course 15/4 for our y value. Now, of course, the next thing to make our change lines, we need our slope, right? So we got to figure out what dy dx is and then plug our number in. So to figure out dy dx, again, this is going to be parametric. Okay, so on top, we have to find the derivative of our y, right? So this would be our dy d theta. So that means in the numerator, we're going to be working with finding the derivative of this part right here. So by product rule, that's going to be 5 times, cosine theta sine theta plus 5 sine theta cosine theta. It's really kind of the same thing, but yeah. There's our product rule. And then, of course, for our denominator, we need dx d theta. So that'll be the product rule of the top one here. So that's going to give us 5 times cosine theta times cosine theta. So I'm just going to write that as squared. And then be minus 5 sine theta times another sine theta. So again, I'm going to write that as being squared. Okay, so we have our derivative. But again, that's just what the derivative is. We need to plug in pi over 3. So our last step is to figure out what is the value of this derivative, right? This is an x, by the way, when we plug our theta value of pi over 3 into it. So if we take pi over 3 and plug it into all these trig functions and simplify it out, this is going to work out to be negative radical 3. Okay, I'll leave the arithmetic to you, but obviously you know the main values that go in there. It does require some squaring and some simplifying, but it does work out to be negative radical 3. So I have my ordered pair, I have my slope, so now I can express this as a tangent line. So it's going to be y minus our y value, okay, equals our slope times x minus our x value. Now for our second example, let's determine, given a polar equation here, where there are horizontal and vertical tangents, okay? So we're only looking for what those are going to be, and obviously as you calculate tangents, right, those are definitely going to be places where they happen. So when I say find them, we're just going to look for locations. We're going to look for ordered pairs where they happen. So obviously let's start with horizontal, okay? So to begin, if we just want to find the horizontal ones, that means that our job is to just focus on where dy dx is equal to 0. So what that really means is, where is dy d theta equal to 0, okay? Now obviously to do this, we have to find the derivative of y with respect to r, okay? Now in this situation, we got to figure out, what does y look like, okay? So in this one, y is going to be equal to our r times sine theta. Now, if we simplify that, that can be, if I distribute, just sine theta and then minus sine theta cosine theta. Okay, so that means obviously when I'm working with this, I need the derivative of that. So I need to do the derivative of this entire expression and set it equal to 0. All right, so if I go ahead and find the derivative of this, the derivative of sine is going to be cosine theta. And then we'll subtract the product rule. Okay, so I'm using my parentheses to make sure I get the sign correct. So the derivative of sine is cosine times cosine. So that's cosine squared. The derivative of cosine is a negative sine times sine. So that'll be minus sine squared. And then, of course, if we simplify this expression, right, that means we're going to get a cosine, theta. And then if you distribute, we're basically going to have a minus cosine squared and then a plus sine squared. Okay, now remember this right here was our derivative. I did not label it very nicely, but this was our dy d theta. So we're going to set this equal to 0. Okay, now taking a look at what I can do algebraically over here, I want to do whatever I can to try and solve for it. Now, because I have a mixture of sines and cosines, what I'm going to do is I'm going to replace my sine squared with a 1 minus cosine squared. That way I can isolate cosine squared and solve for it. So that means this is going to be cosine minus cosine squared theta plus, and again, I'm going to replace my sine squared with 1 minus cosine squared theta. So what that lets me do, of course, is I can combine my terms. So that means over here I have 2 cosine squared thetas. And by the way, I also divided by -1 because I want a positive leading coefficient here. And of course, my cosine theta, when I divide by -1, gives me a negative cosine theta here. And again, the 1 divided by -1 is -1. Okay, so I put the two squares together and moved everything out, or divided by -1, however you want to look at it, but this is what I got to. And that helps me because now I can just use some factoring. So this factors to 2 cosine theta plus 1, and then of course cosine theta minus 1. So that means I got to solve for all the values that make this happen. So looking at the first term, 2 cosine theta plus 1, well, if I solve for 0, that's asking me where cosine of theta is equal to -1/2. In the other one, I'm looking for where cosine theta is equal to 1, when I set that equal to 0. So if I look at the values where cosine is equal to -1/2, that would be at 2 pi over 3, 4 pi over 3, and cosine is, of course, equal to 1 at 0. So I got those locations. Now, I'm actually going to hesitate to make ordered pairs out of them yet because, while I do know that this is where dy d theta equals 0, I can't really say it's going to be a tangent yet because I want to double check that it's not a place that's a determinant. So I'm going to go ahead and calculate where the vertical tangents may happen at, and any overlap I got to throw out, because any place that both dy d theta and dx d theta simultaneously equals 0, that's a place where the derivative doesn't exist, and clearly I won't have any tangents. All right, so I need to make sure we're checking that. So this is potentially where my horizontal tangent is going to happen at. So let's find our vertical. Okay, now we're going to do basically the same idea, except this time obviously we're looking for where dx d theta is equal to 0. Now our x's, again, is going to be our r value times our cosine. So again, if we distribute, x is basically equal to cosine minus cosine squared, something I think is a little bit easier to work with. All right, so let's go ahead and figure out what dx d theta looks like. So the derivative of cosine, of course, is going to be negative sine minus, and then this is kind of like a chain rule, so it's going to be 2 times cosine theta times negative sine theta. And we want to clean that up a little bit. So what I'm going to do is I'm just going to say this is negative sine theta, and then of course we'll just say that's plus 2 sine theta cosine theta. Okay, so we got set equal to 0. So doing so, I can factor out a sine from there, and that will leave me with my 2 cosine theta minus 1, and that can just set each one equal to 0. So I need to solve for where sine theta equals 0 and where cosine theta equals positive 1/2. So again, just setting each one of these pieces equal to 0. Well, when we talk about where sine equals 1, well, that's going to be at 0 and at pi, and cosine theta is going to equal 1/2 at pi over 3 and at 5 pi over 3. Now again, these are places potentially where I have my vertical tangencies. But before I can really say, where my horizontal and vertical tangencies are, I need to double check if there's any place where both horizontal and vertical are simultaneously equal to 0. Now looking at the list here, definitely there's one spot, and that is here at 0 that they both share. So that means that at theta equals 0, that means the derivative, right, in this case dy dx, that's going to 0 over 0. So that means, yeah, there's nothing going on there. That's not smooth, right? So that means because obviously it's a place where it's not smooth, it's not horizontal or vertical. Okay, we're throwing that out. So if our answers, right, we want to write down where we have horizontal tangencies. And again, we want to express these as ordered pairs for location. So one of them is going to be when we have a theta value of 2 pi over 3. Now, of course, to figure out what the r value is, we can just plug that right back into the original equation right here. Doing so would give us a 3/2. It also is going to happen when we are at 4 pi over 3. Okay, and again, plugging that in should give us the same thing, 3 pi over 2. Sorry, 3 over 2. So the next piece then is let's identify our points where we have our vertical tangents. Okay, so if we want to figure out the points where we have the vertical tangencies, that means again it's going to happen at pi. And again, plugging that into our original equation is going to give us a value of 2. It also happens when we are at pi over 3. Okay, and then plugging that in, of course, is going to give us a value of 1/2. And lastly, at 5 pi over 3, if we plug that into the original equation here in polar, it's going to give me our value of 1/2. So these are the places where horizontal tangents exist on the curve. These are the points where we have vertical tangencies happening on the curve. Now, the last thing I want to talk about is identifying when tangent lines are occurring at the pole. So the idea that we're tangent to the graph, but we're also passing through the pole. Now, in order for that to happen, we need to make sure, first off, the place we're happening does give us 0. Okay, we have to be at the pole. However, the derivative cannot equal 0. Okay, so that's kind of the conditions to make this happen. So assuming that the angle we have is giving us a value of 0, putting us at the pole, and the derivative at that point is not equal to 0, then this line, okay, so theta equals some value, is going to be tangent to the pole, at the pole to that graph, okay? And again, tangent equals a number, theta equals a number is always going to be a tangent line, or even a line in general, because in polar, when you're graphing, if you don't care about r, and all that matters is that all the points have a certain theta, you're always going to be creating a line. Okay, and again, this special line does pass through the pole because we know it makes 0. So obviously to do this, we have to check a couple things. We have to figure out where do we equal 0, so we have to solve our r for 0, but then we also have to make sure we know where the derivative equals 0, and then throw any of those points out, just make sure they're not the same. So step number 1, we need to set r equal to 0. We got to figure out where that's going to happen at. Okay, so that means we're going to take 0 equals 2 cosine 3 theta. Now, doing so obviously means you got to solve the equation, which means for this to be 0, the angle 3 theta, that has to equal all the places where cosine equals 0. So like pi over 2, 3 pi over 2, maybe 5 pi over 2. I'm listing out enough to make sure I stay within one period because, again, solving for theta does mean I have to divide by 3. So it looks like we got pi over 6, pi over 2, and 5 pi over 6. So we got that going for us. And we're going to go there. And by the way, I should point out, one of the reasons I also know that I'm kind of looking for just 3 of them is because if you think about what this graph looks like, this is 2 times cosine of a multi-angle here. This is a rose curve. And because it's, a rose curve is cosine, that means that, first off, it's got 3 petals. So if you think about what the picture looks like, we're going to be starting somewhere out here, and we're going to have 3 petals. So I'm just going to make a generic picture. I don't know if that's what it looks like necessarily. But because there's 3 petals and I start on the outside, right, of my max R value, that means I'm going to pass through the pole 3 times as we sketch this, which means I know there's only 3 places this is going to happen. Because obviously I could keep going with many different angles, but that's why I know I'm stopping at 3, right? This is a rose curve, 3 petals. I'm starting on the outside because it's cosine, so I pass through the pole 3 times. So I know there's 3. Now, before I say, hey, these are the places obviously where that's going to happen, again, I got to double check that the derivative of r doesn't equal 0 at these points either, because that can't happen. We have to be at the pole but not have the derivative equal 0. So now we're going to check r prime equals 0 and see if there's any overlap. Now, the derivative is, going to be a chain rule here. So we got -6 sine 3 theta. And again, we're going to solve that for 0, which means, of course, we need 3 theta to equal 0, or I should say be the angles that make sine equal 0. Okay, so that's obviously going to be at, 0, pi, 2 pi, and so on. I'm only going to go about that far because obviously that's all I need to do, because that's going to tell me I'm going to have a 0, a pi over 3, and a 2 pi over 3. And when I'm looking at these places, yeah, that doesn't work for any of these. Now, another thing I could have done, to be honest, was I could have just said, you know what, let's not even worry about doing this. What you could do is just take the places you're considering and just ask yourself, does that, when I plug it in here, make this equal 0? And again, none of those would make it equal 0. So we don't need to worry about that at all. So that means, obviously, when we talk about tangent lines, these are going to be the places where those tangent lines happen. Okay, so from a linear perspective, our tangent lines that are going to be passing through the pole can be written this way. Okay, so one of them is obviously going to be theta equals pi over 6. Another one is theta equals pi over 2, and theta equals 5 pi over 6. Okay, so that means obviously if on the curve, assuming it kind of looks like this sort of rose curve, that means it's going to be going on those directions from the pole.